Uh, yeah, so today I'm going to talk about some work from my PhD on defining and evaluating the predictions of joint species distribution models. So this is done in conjunction with my supervisors, Nick, Guru, Reed, and Mick at the University of Melbourne. Uh, so JSDMs have been a fairly hot topic in the literature for the past few years, but a lot of the work is focused on um, implementing new methods or extensions to these methods to account for things like traits or phylogeny, whereas prediction as a topic for JSDMs has only recently started to be explored. So for single species models, we're used to seeing prediction outputs like this. So this is a prediction for the Carolina wren in North America. But in single species models, they're not accounting for the interactions between species, or if they are, it's only unidirectional responses like using additional species as predictor variables, or constraining the prediction to only sites where known host species occur. And community level predictions generally involve just stacking multiple single species predictions together to get some sort of estimate of species richness. But these sort of predictions don't account for the impact of species co-occurrences on the community assemblage process. So in come JSDMs, but the question is, what can JSDMs do that single species models can't? And then how can we evaluate it? So for single species models, we have a single response variable to consider, which is just the target species. But for JSDMs, there are multiple response variables that are all potentially correlated with each other. So I've got a few equations throughout this presentation because it's a statistics conference, so I won't dwell on them too much because the visual representations are much more useful. But the point here is that, so the probability of species A and B jointly occurring at a site can be expressed as the conditional probability, well, the product of a conditional probability and a marginal probability for these species. And here the two lines are equivalent because it doesn't matter which order that you marginalize a species out. And the same thing works if you go into a scenario with more species where you marginalize out one species at a time. So at different steps, you can have a single species conditional on a joint probability of the remaining species. But that's for a discrete response variable case. So ones or zeros for presence absence. JSDMs use a latent variable parameterization. So a species here, so for species J at site I, its presence if a random draw from this latent variable parameterization is greater than 0, which is the area under the gray area under the curves here. And it's probit regression. So the variance is constrained to 1. So you can see that for these two different species, the shape of this distribution doesn't change. It just shifts across the x-axis. So to get the probability of a species occurring, you actually want the probability of a draw from this distribution being greater than 0, which you can calculate by taking the integral to calculate the area under the curve. But with these models, what we actually have is a big multivariate normal distribution where we now have a vector of means, and the correlation structure between species comes from either a full rank or a latent factor approximated low rank correlation matrix that's estimated during model fitting. So now if we take a draw from this distribution, we take a single point. So if our draw from this distribution falls in this top quadrant, then both species are present. If it falls in the bottom left quadrant, then both species are absent. So what this means is that when we take a draw from this, we're getting a community assemblage. So here, so we have like a 16% chance of both species being present, 31% of both species being absent. So what our equations actually look like is that, so the probability of these two species both being present, actually the probability that the latent variable draw is greater than 0 for both of these species, which looks like this. So again, I'm not going to dwell on the equations too much. But it's important to know that even though we have this multivariate joint distribution, these marginal distributions for each species are still there. And you can see that the numbers for these correspond. So species A here has a 69% chance of occurring. And you can see if you add up the different possible assemblages where the species is present, if we add up these two values, we still get the same sort of number. So what this is used for is that we can actually condition our predictions on the known occurrence of species. So we have the full distribution on the left, but on the right here, we've truncated this multivariate normal distribution on the known occurrence state of species A that it's present. But because the area has to sum to 1 because it's a probability, it actually updates the probabilities for our community falling into either of these assemblages. So you can see that when species A is present, there's actually a higher probability of species B occurring than species B has if you're drawing from the full distribution. So what we have is that there are actually 5 different types of prediction that we can do with JSDMs. So we have marginal predictions, which are species specific. So this is where you're trying to predict species A without having any information or ignoring any information on the remaining species. We've got a joint prediction type, which is at a community level, which is where you're trying to predict all of the species simultaneously. And then we have our conditional predictions. So a standard conditional prediction would be trying to predict one species knowing the occurrence dates of all of the others. And that's a very rare scenario in ecology, so we're not going to cover that one. But what I will talk about are conditional joint predictions, where you're trying to predict a full assemblage conditional on knowing the occurrence of a small subset of your species, or a conditional marginal prediction, where you're trying to get your species-specific probabilities for one species with some information about a small subset of other species in the community, but without any other information on the remaining species. So once we have our predictions, we also want to figure out how to evaluate them. So we've defined 5 different classes of evaluation metrics. So the first couple will be familiar from single species models. So threshold independent metrics like AUC or RMSE, threshold dependent metrics like true or false positive rates or Cohen's kappa. So these all operate at the species level, but now that we're in multivariate space, this opens up the opportunity to use some metrics that operate at the community level. So we can use community dissimilarity metrics like Bray-Curtis dissimilarity or Jaccard's index, which evaluate how close our predicted community assemblage at a site is from what's actually there. We can look at species richness, and we can evaluate that regardless of whether we've predicted the correct species at a site, have we correctly predicted the right number of species? And then we've got some likelihood metrics, which are assessing our model fit. So I've done a big prediction comparison. I've fit 6 different joint species distribution models that are a mix of full rank and latent factor approximated correlation matrix models. I fit two stacked species distribution models, one which is just the standard stacked probit regression, and one which is the CSAM framework, which constrains your predictions. I've done this across 22 data sets, cross-validation, and 8 prediction types because we've run our conditional predictions under 3 scenarios with a low, medium, or high prevalent species. And then we've used up to 32 evaluation metrics over these 5 classes, depending on the prediction type. So I did that, which leads to doing a lot of this. So I moved to a supercomputer, which means I get to do a lot of this. So what do our predictions actually look like? So on the left, I have my actual known presence absence values at a site. So anything here in black is where the species was present. So for my standard marginal predictions, which is species level, they look pretty good. We're getting similar sorts of distribution here. But when I condition this prediction on the known occurrence state, I get something that's much closer to what's observed. It's really hard to see a huge difference on a probabilistic prediction. It's much clearer on something at a community level. Um, so here, so this time I've taken a heap of random draws from this distribution at a site. So the top row here is my observed values. So I had 3 species present. You can see that for the joint prediction, while we're quite often predicting those species, we're also getting a lot of extra species in the predictions. But for our when we condition that on the known occurrence of one species, we actually are able to reduce a lot of that over prediction. So as far as a comparison, because how well do these models compare, I've generated some heat maps like this. So each concentric ring is a different model, and each ray is a different metric. So all these metrics are evaluated on different scales. So some are 0 to 1, others are negative infinity to infinity. So we've expressed these as a relative performance measure. So all of these rings are a JSDM and relative to the standard stack model in its performance. So anything in blue, the JSDM has performed better than the standard stacked model. Anything in red, the JSDM has performed worse. So sadly, we are finding that the JSDMs aren't predicting as well as a standard stacked model. But at the same time, because we're on a relative scale here, it does exaggerate a lot of these differences. So you can see here that most of the cases where the JSDM seems to be performing rather poorly are all metrics where the optimum value is 0. So the better the models perform, the more exaggerated this relative difference is. So bias, for example, comes up looking really terribly for JSDMs. But in actual fact, this is like comparing 0.0002 against 0.0004, and showing up as a massive difference. But the promising thing here is that the likelihood metrics are suggesting that JSDMs are still better fit to the data, even if something is not holding up well with the predictions. So across all of the species level predictions, so the marginal one is that we're from the previous slide, the top left, and then my 3 different conditional marginal predictions. We can see that by conditioning our predictions on species, that for in the low and medium prevalence predictions, we're actually improving all of our predictions compared to the standard stacked model. So this is a really useful development. But you see when we condition on a high prevalent species, we are getting slightly worse community level predictions, and we're still investigating why that is. But you can see that for species level metrics, we're actually getting virtually no difference. AUC across all models is within 0.01 for everything. And for our community level metric, something like Kozinski's index here, we're actually not seeing a very large difference in performance. It's just exaggerated by this relative measure. So I'm going to quickly skim over the joint metrics because I'm nearly out of time. But you can see that when we're doing community level predictions, we're actually not getting a great performance from the JSDMs. This outside blue ring is actually the CSAM model, which is outperforming all of the JSDMs and the standard stacked model. But if we condition our joint predictions on the known occurrence states of other species, we are seeing a big improvement. So I'm out of time. So if anyone has any extra questions on any of these, feel free to chase me up, either in the Slack threads or any other time during the conference. So that's it for now for me. So thank you very much for listening, and I'll answer any questions.